Thank you for joining, and thank you for your interest in smoke. Something I've been very interested in, not just from prescribed burning, but the wildfires themselves. And before I get too deep into this presentation, I do want to acknowledge that I had a lot of help in developing the techniques and the methods that are being presented today. Brett Anderson, just a brilliant atmospheric scientist, air quality modeler, no longer works for the Forest Service, but now works for the BLM. Spencer, Chris, and Sarah, just great AFMOs, fuel specialists in Western Oregon, and had a lot of help from those folks. I really have a lot of admiration for our fuels folks out there implementing on a day-by-day basis. Daisy Mercer, just another person who left the Forest Service now with BLM, and she helped me with some of the R scripting, and was just a wonderful person. Oftentimes we don't recognize, but I want to give credit to a previous supervisor of mine, Darcy McDaniels, who was really supportive in this research. And so Darcy left the Forest Service and went into like cryptocurrency. So took a really different path now after working in fire science for many years. And Janice Peterson, who was just a great mind, a great writer, critical thinker. I always appreciate Janice because we never thought the same way. So I always appreciated having a different thinker, different perspective who would challenge me. So oftentimes people run through these acknowledgements, but the people we work with are so important. I just want to take a minute to recognize those. So motivation for the study. I love this photograph because I so much identify for what I think this person is thinking here. And that is many of us who during wildfire live in these communities and are impacted by the smoke. It impacts our lifestyle, our health, our mental health. It impacts our communities, our towns, our tourism, the economies. A summer with wildfire smoke, if you've lived through one of these, it could go on for months, certainly weeks, and really could ruin a whole summer for us, or whatever your fire season is, if not summer. And so while we do a lot with wildfire already in terms of deploying air resource advisors on incidents, by forecasting of smoke, monitoring smoke, public messaging to help people modify their behaviors, I asked myself, isn't there more we could be doing? Are we doing all that we can? And that was my motivation for this study. So I wanted to share with you a few ideas I have about what more we could be doing. Perhaps you have others too. So in this approach, I think the concepts are fairly simple, but the implementation is more complex. So it's really about like, if we knew where the smoke was coming from into a community during our wildfire season, that helps now narrow down what we might be able to do about it. And so smoke doesn't move, or air doesn't move into communities equally from every direction. Not typically. Usually there's a dominant direction or two. Sometimes it differs between day and night. And sometimes we've all looked at windroses and can understand that. This approach takes a little bit more sophisticated approach than just looking at the windrows. Get into that in a minute. And then, but then if I knew where those pathways were, then I wonder what management options do we have along those pathways to reduce wildfire smoke? And then how much could we really reduce? Does it matter? And then I'm going to use a case study to demonstrate that. And then I was also asked during this talk to talk about the applications, as many of you are in decision-making positions, managing the land. Maybe some of you might be agency administrators. I don't know, but so I have a couple, a few different aspects to present on the application side. So when I talk about what is a frequently impacted community, not all communities are impacted equally by smoke. Here is a map we've created for the Pacific Northwest based upon air monitoring locations that are run by state air quality agencies. So we know the data is of pretty good quality. And what we mapped out here is on average for this 5-year period of 2015 to 2019, how many days did each of these communities experience unhealthy air quality due to smoke? And the size and the color of each circle there is related to the number of days of impact. And on the west side of the Cascade, you'll see a lot of green or light green or yellow, meaning they might on average only have like 1 to 3 days of air quality, bad air quality due to smoke. Certainly Portland, Seattle this last summer had worse, had 8 days. But you could see a cluster of larger circles that are more red in color in southwestern Oregon, Klamath Falls, Medford, Ashland, Grants Pass, Shady Cove. Those all could experience on average 13 to 18 days. So we're getting closer to 2-3 weeks of bad air quality on average. Certainly on some years I've seen 40 days of bad air quality in Shady Cove. Oak Ridge, Oregon had 37 days this last summer. Another area that's pretty frequently is on the east side of the Washington Cascades, near Wenatchee and Twist. When we went through up in Chelan, they typically have about 2 to 3 weeks of unhealthy air quality due to smoke. Bend, Oregon, and on the east side of the Oregon Cascades also gets fairly frequently. But as you move further east, not quite so much. Somewhere between those communities and a little bit in more than we see down the I-5 corridor there. But since we're talking outside the Northwest too, to some other audiences, I did try to find some other data that would be indicative of how frequent bad air quality occurs to smoke. I found this map that was produced from another group out of a university here. And this is based upon satellite information, not ground-based information. So you can see a lot of smoke over the Midwest there. And that's not necessarily at the ground because it's not based upon ground monitoring. It might be at the ground, but look at the Sierra Nevadas of California. Quite a bit of smoke down there. Xander, where you are in Santa Fe, a medium amount there. Montana, Wyoming, Idaho, quite a bit of smoke too. So if you want to, there's data you could look up to find out exact numbers in your communities. I've contacted some of my colleagues in other regions, but nobody, to my knowledge, has produced those ground-based maps like we have in the Pacific Northwest. So I mentioned, what are these air pathways that are common during wildfire season? In Pacific Northwest, during the period of time I looked at, wildfire season typically started as early as mid-July and extended to the end of September. And so I looked at that time period. And what I did is I used a model that is models air pathways, or let's think about this like a backwards trajectory model. So normally in a forward trajectory model, we would have a fire with its smoke emissions, and we would take in ingest information from a meteorological forecast model, and it might anticipate what the wind speed, wind direction, atmospheric stability is for the next 6 hours, and eject that plume in that direction at that rate forward, and in the vertical up or downward motion as well. And then it'd take the next forecast period and look at another 6 hours, et cetera. Well, in this case, we start where the smoke ends up. In this case here, I have an example for Medford, Oregon, which is the black star, where all those lines converge in the top part of the graph. And basically, we take those same meteorological models and we apply them backwards in this high split model. And that's a NOAA product from the National Oceanic and Atmospheric Administration. And I ran this model 4 times a day to capture the diurnal variability. And so here's an example for one day. On the top portion of the graph, you could see the differences in horizontal trajectories where smoke came from that moved into Medford, Oregon over the last 36 hours. The bottom part of the graph kind of shows that vertical distribution, and it starts from the left and goes backwards to the right. So we ran it to midnight, 6 p.m., noon, and 6 a.m. local time. This is expressed in universal transverse time, so it's UTC. But you could see like the red line there starts aloft, and as you move to the left, it comes down to the surface. Same with the purple or bluish line. The light blue also starts pretty high and moves down. But when we get to that green line, You can see that's more 6 a.m. arrival. And that's, overnight. We have those temperature inversions, and smoke usually doesn't, it stays closer to the ground. And this model seems to capture it pretty well, which is one of the reasons I like this model. And we get these very unique trajectories. So we ran the model with this high resolution rapid refresh model, the HER model, which has for those of you who know about meteorological models, got 3 kilometer, very fine resolution for a meteorological model. So it could capture a lot of the drainage flows along river valleys in the complex terrain. It captures the peaks and does a better job of characterizing the complex terrain and the air movement in complex terrain, much more so than like a wind rose. I ran it backwards 36 hours because I wanted to kind of focus on local influences. I started at 100 meters off the ground sampling height. And like I said, we ran one trajectory every 6 hours. And when you do this over the course of a wildfire season, 4 trajectories a day, from mid-July to the end of September, that's 77 days. And then I did it over a 5-year period, you get 1,540 trajectories. And when you plot them all out, you get that big map full of lines that it's really hard to tell anything about it. So we used a GIS technique in which we put a grid over this with 3 kilometer spacing, and we count the number of lines that are in each grid cell. Put a little buffer around each grid cell to help smooth the data out a little bit. Count how many lines and the distance of each line in the grid cell and its radius of influence. And then what we could do is we could color code those in a raster image and project that. So let me explain this a little bit. You'll see a lot of these types of graphs here. So when we start at the blackish area, that all lines, as you saw, converge into the area that or the community of interest. We're going to have the most number of lines. Let's call that 100% of the lines will converge on that grid cell that represents that community. But as you get out further and further, you have fewer and fewer lines that are in each grid cell. So we could characterize those as a relative percentage of each of the total amount. And this, after playing with the frequencies quite a bit, I found this kind of coloring allows one to see sort of these patterns of influence into a community without being overly extensive. When we get down to less than 3%, we get lines everywhere. And that wasn't really meaningful. So I removed the coloring. So when you look at a map like this, I don't want to infer, or it should not be inferred, that smoke does not move into here like Medford, Oregon from the south. It just means it doesn't happen nearly as frequently as some of these other directions. We're playing a probability here, so to speak. And what we see here is during this wildfire season, during this period of analysis, smoke mostly moves from the northwest into Medford to the south, but we have these fingers that come across some of these topographic features. To the southwest, there's a part of it that moves up the Highway 199 corridor. We capture to the upper right towards the northeast up the Rogue River Valley, the upper Rogue, and a little bit further north up the South Umpqua River. We're capturing some of these drainages. Well, when you do this across a lot of communities, you could see that very unique patterns become evident. Look at that pattern around Seattle, Washington there. You could see a very unique pattern of airflow around the Olympic Mountains, either to the north or to the south of the Olympics that move into Seattle. Out there in eastern Oregon, in La Grande, you could see a distinct pattern from east to west as air moves through the Columbia River Gorge and blows towards the east into La Grande. As you move into Northern California, we can see more of a north-south pattern, like into communities like Redding. And along the coast, more of a northerly flow into the communities along the coast during this wildfire season. So very unique patterns. Again, there are more probabilities, which I think gives the analysis a little bit more strength than looking at any one individual location. What can you do with this information? So I'm going to give you an idea here. This is application number 1, I call it, and that's during wildfire season. And during wildfire season, if we get a fire that begins on the landscape and we could overlay the perimeter of the fire with these trajectories, I could get an idea of whether or not we're going to have long-term smoke impacts into the community or not. Well, that might be very helpful. Let's say you're an agency administrator who's very concerned about your community and its members, and that might be either you want to request more resources, including ordering an air resource advisor. You want to coordinate with your community. Some communities, like, they'll have resources that could bring in portable, high efficiency particulate air filters for those who don't have the economic means to protect themselves, or air conditioning units to filter out those things. That might affect community events, all sorts of things. But if we know we're going to get long-term smoke impacts, that's an opportunity there. And so I tested this out for the first time during this last fire season. So here on this map, you'll see a showing in red shading where we had the large wildfire incidents for 2022. And so, like I said, we could overlay these. And I just picked a few of these trajectories to look at how we did. And let's start in the middle of Oregon here in the Cascades. And we could see that that was a Cedar Creek fire. And you could see it overlaid the yellow area. That was a frequent air into Oak Ridge, Oregon. Oak Ridge had 37 days of unhealthy air quality. Now recall the maps that I created went through the end of September. But this 2022 was an unusual year because we had fire season go up to October 24th. And during the month of October, we had high pressures dominating our weather pattern for the season. So a lot of subsidence, very poor ventilation, a lot of air quality problems. So even, I'd like to extend these maps out to consider October in the future. But even without that, I thought it did pretty good. You look up in central Washington, in the community of Wenatchee, they had 21 days of poor air quality or unhealthy air quality. There were 3 fires up in that area that were within this frequent air pathways that put smoke into Wenatchee during that time. Out in Enterprise in northeastern Oregon, we had quite a few fires around that community up in the Eagle Cap Wilderness and Hell's Canyon area. But they were just, at most, only one fire was on the edge of that yellow. And consequently, well, we'd say Enterprise only had 7 days, about a week. And down in southwestern Oregon, that Rum Creek fire just north of Grants Pass was in the yellow. And Grants Pass had 6 days of unhealthy. So, looking at a few of these, we're starting to get some credibility. This has, I think, doing pretty good. It's not the end all, but I think it's a really good start for this. And so I do get calls during the wildfire season, and I think this is helping us in terms of strategizing for how to approach fires and deal with the smoke issue during wildfire season. But that's just one application. I do want to talk about fuel treatments because a lot of our land management decision-making deals with where we're going to do fuel treatments, how we do fuel treatments, what do we treat, et cetera. So what I decided to do is look at a case study here. And I chose a fire, then we're going to compare emissions for 2 scenarios. One is an actual real scenario that happened with this fire. And in one of the communities that most had some of the worst air quality it had in the 5-year period. And so I'm going to compare that with untreated fuels. And then if the fuels were treated, what we would have seen based upon model predictions, if those fuels were treated and a subsequent wildfire occurred, we're going to quantify how much the air quality would have changed in that community. And I think there's a lot of lessons to be here. So the technique, what I use is just a simple ratio method. So the subscript 1 refers to untreated. So E is emissions and C is concentration. So what I'm saying is the emissions from an untreated scenario where wildfire comes through is related or proportionally related to the concentration, the downwind concentration in the community, That's proportional to if we change the emissions in the same scenario, we would see a proportional change in the downward concentration. And the assumptions there is the plume rise is the same, the meteorology is the same, the atmospheric chemistry are all the same between those two scenarios. In reality, there might be some differences here, but this is a nice, simple way of addressing this issue. So the case study I selected was from this community of Shady Cove, Oregon. Shady Cove is probably the most frequently impacted community down in southwestern Oregon. In 1 year, I've seen 40 days of unhealthy air quality in this community. And it's a high recreation community too, a lot of rafting trips, fishing trips in the Upper Road River. And on this day of August 2nd, 2015, it experienced the highest concentration of fine particulate matter, that's particulate matter PM 2.5 refers to micrometers, and that means it gets really deep in your lungs. And so the National Ambient Air Quality Standard for PM 2.5 for a 24-hour average is 35 micrograms per cubic meter. So this is 295, so considerably higher than what's considered healthy or acceptable by EPA here. So doing some analysis, I was able to determine, plotting all the fires on the landscape on a given day and then running back trajectories, looking at the fire history in detail, and then doing some forward modeling. I was able to determine that the smoke in the community came from two fires. Stouts Creek Fire, which was 32 kilometers northwest of Shady Cove, and the cable crossing fire, which is further away, 77 kilometers away of Shady Cove. One was on each day, let's see, Stouts Creek had 10,700 acres burning at that time, and the perimeter on the cable crossing fire was only a tenth of that, roughly, 1,574 acres. And so about 90% attributed to Stouts Creek and 10% from cable crossing. So now I want to talk to you how we calculate emissions. And when we deal with smoke, we deal with fuel models like fire behavior specialists do. Although we don't use the same models, fire behavior specialists are interested in the fuels in terms of predicting rate of fire spread and flame length, things like that. We talk about smoke, there's other aspects of the fuels that become very important. Think about tree stumps. Think about those logs and the duff. They might not add that much to a fire behavior model, but they add a lot of smoke to our smoke models. So basically, I used a tool that was developed by Susan Pritchard and Roger Ottmar out of the Fire Environment and Research Application Lab. So that's the U.S. Forest Service Pacific Northwest Research Station, Seattle Fire Lab, those folks there. And they've developed this tool called FFT, or Fuel and Fires Tool. And basically allows you, I could overlay in this tool a perimeter of those fires. And let's say, even though it looks like the state of Maine, it's not. This is just, let's say, a fire perimeter here in the upper right-hand corner. And there's different fuel beds in these within the perimeter. And that's denoted by these different colors. And this is the Fuel Classification and Characterization System, FCCS. You can find this in Landfire, pull it in GIS. And what we get is different fuel types in here. And for example, I just have an illustration. When I say different fuel types, consider something like in this upper left-hand corner, we got a hemlock fir, Doug fir forest, a lot of down wood. That's very different than like a sage steppe fuel bed that you would see out in Eastern Oregon, or like in the bottom left figure there, there's a ponderosa pine sagebrush kind of forest of Eastern Oregon. And in each fuel bed, we have 6 different stratum of fuels to consider: the canopy, to the shrubs, to the down dead wood, lichen litter moss, to the ground fuels, the duff, and the litter. And each of those has a designated fuel loading that you could modify based upon your observations or come with a default. And when you give the model a fuel moisture, the wind speeds, and the slope topography, it'll predict the fire behavior and fuel consumption. And it'll apply emission factors to that fuel consumption to give you an emission rate. So when we do that, here's some examples. how those might change under a fuel treatment. So the images on the left were taken from just an example in Central Oregon, Black Butte Ranch, where they did a thinning and prescribed burning project. So the figure on the left is what the landscape looked like before thinning and burning. The middle figure is after thinning. You can see some of the tree, the density of the bolls have thinned out a little bit, but there's still a lot of ground fuels with the shrub. And then when after you apply prescribed burning, you can see the canopy is raised, you can see the shrub decrease. There's less needles on the ground and duff there. So talking with those fuel specialists, we looked at each of these layers and we decided how much each reduction we're going to have in each of these vegetative strata. And you can see here that like the down dead wood were reduced by 50 to 60% was the goal there. Shrubs and herbs by 50%. The duff and needles were down by 40%. Not that much reduction in the canopy, so we didn't want to kill off the trees, obviously. No changes to the snags or the ladder, but we did eliminate the ladder fuels here. So that's sort of a typical treatment you would see in this was on the Umpqua National Forest, so a forest of Western Oregon. And what you might have for a fuel treatment in your area might differ. So this is a really interesting slide graph to me. There's a lot of information here. So let me try and explain this one a little bit. We have within the fire perimeter 4 different types of fuel beds were identified. Let's just call them 2, 9, I think that says 16 and 38. We won't get into their names and things like that. And then under each one, we have U for untreated and T for treated. And in each bar there, you see 6 different colors representing the contribution for the blues, the canopy, the yellows, the down dead wood, greens, the duff, or the ground fuels, and their shrubs, herbs, and like litter moss as well. So the first thing to notice, is on the left-hand side of the screen, it's the emission rates, the pounds per acre. So notice like fuel beds 9 and 2 emit quite a bit more smoke when they're burned than fuel beds 16 and 38. Yeah, almost 3 times more. And where does that come from? Well, look, there's a lot more down dead wood on the ground that gets burned during those, as well as duff. And even in the canopy, there's quite a bit more. But when we do the fuel treatments, we could see that we're reducing mostly the wood and mostly the duff, not so much the canopies, changes, and others. So that's where we're getting our big reduction in emissions. Now remember, these are emissions during the prescribed burn. There's if a wildfire were to burn through the treated area afterwards, and how much smoke would be generated. Okay, so let's move on to the next slide. So let's look at the results. So let's look at the difference between the emissions and the downwind concentrations in Shady Cove between, just from the Stouts Creek fire, between a treated and an untreated scenario. There we had emissions from untreated, a little bit over 3,000 tons. But when we ran after we treated and the wildfire came through, there was a reduction from that down to 1,660 tons. That's a reduction of 1,365 tons. Well, proportionally, that's a decrease in concentration from the 295 that was observed. We would have only had 162 micrograms per cubic meter. Well, think about this for a minute. Does that make sense? And what I think about is, yeah, it does make sense, because when we have wildfires and if our forests were within their natural range of variability, not overstocked, and we operating during our normal fire retreatment, there would be a certain amount of smoke that would be natural. That's what I call that 162, so to speak. It would be more of our natural amount of smoke. And the extra 133 tons is sort of what I call the additional smoke from not having fire on the landscape as much as would be natural. So there's a natural amount of smoke and there's an unnatural amount of smoke, how I think about it. When you do the calculation, that's a 45% reduction in the smoke just from that one fire. But I also recognize that, when we have wildfire season, we have smoke in a community, it might not just be from a single fire. There might be several fires that contribute to that. Well, and not every fire is going to run into a fuel treatment. So here I just ran the case, how much would we reduce the air quality in Shady Cove? Let's say 90% of the smoke came from the Stouts Creek fire, which was treated. Let's say Cable Crossing fire wasn't treated. There, we would get, when we apply the 90%, we drop that 295 down to 265 from the Cable Crossing. We add in, I'm sorry, from the Stouts Creek. We add in the background that 10% from the Cable Crossing, and then the concentration is not reduced as much. So it's only a 41% reduction, but still that's substantial. That gives me an idea under this one case scenario, how much we could reduce smoke if we did fuel treatments in these targeted areas and they intercepted a wildfire. Well, how do we use this information? Well, so here's, I'll have a couple examples to show you here. So again, back to Southwestern Oregon, where I live. This is a case, this purple outline here is the Rogue Basin. So this is Crater Lake National Park. In the purple in the upper right, there's three figures here. So I'm referring to the upper left figure. And if you look in the upper right portion of that figure, you will see a rectangle with this purple with a blue circle in that. That's Crater Lake National Park. And the Rogue River runs all the way to Gold Beach on the west side of the coast of Oregon there. And all these communities are located in the valleys in between. So here's the frequent path in the upper right figure now, figure B, frequent air pathways into Ashland, Oregon, where they're doing a lot of work to restore the forest out there. And we can see that, again, the frequent air pathways up to the north, very similar to Medford, had that finger going into off to the left and then to the south. And then in the lower right, the lower left figure, I plotted the departure from natural range of variability for the vegetation condition class. And I picked out some of the more departed conditions indicated that red wine kind of color that's there. And if I had more GIS skills I could do really quickly, I could just take mask image of that. But what I would see here is if we really wanted to do a lot of reduction in fuel treatments to reduce smoke in Ashland, what I'd want to do is focus on these areas that there's not so much departed conditions on the national forests within the Rogue Basin, but it's more on the BLM and private lands that are in the yellow and the white. So I'd focus on there and along the Highway 199 corridor. Well, here's an example for Grants Pass that has a different kind of frequent air pathway configuration to it. Same information, but here I focus primarily to the north of Grants Pass, a little bit to the northwest, and again to the southwest along that corridor, along that 199 corridor towards Cave Junction in Northern California. And not so much to the south and to the east, because you really won't get a high probability of reducing smoke in those communities. So if you had these kind of plots, that have been prepared for these communities, you could use them in a GIS application to help with your land management requirements. And then the third consideration that I'd like you to think about is we're not required to do this, right? There's not a law that says thou shalt reduce smoke. EPA is not telling us to do that. We kind of get a free pass with wildfire smoke, but with our prescribed burn smoke, we don't, at least not for the time being. So I think about like when I go out and talk about fuel treatments and reducing smoke with the fuels programs specialists in the forest, I hear that, well, I want to focus on which vegetative strata are causing the most amount of smoke, and that's the downwood and the dove. And then, but we've got to leave a lot of that for wildlife consideration, wildlife habitat. I get that very much so. However, I think smoke has been absent from the conversation. We haven't had a place at the table, and I'm not saying we need to remove all that. But when we look at the treatments, let's look at how much sound wood we have and what are the targets being imposed. Can we do a little bit better than this or not? And is there a place for some communication and discussion around these in terms of how much smoke should be done, how much smoke we want to reduce during the NEPA process in our fuel treatment? So Wish I had a place at the table. Don't always, rarely do, but maybe that's a place we want to have some more discussion. And so in conclusion, I think these air pathways could be helpful to help us focus on specific areas, not just during wildfire season, but also for land management planning. We've seen that, at least in one case study, we could substantially reduce the downwind air quality impacts. And depending on where we do the fuel treatments, the types of fuel beds and the vegetation layers that we're focusing on, they matter. And I do want to mention that for all these layers that I have for Pacific Northwest and Northern California, I'm working with our ArcGIS specialists. We'll put them available on ArcGIS online, AGOL here very soon, probably next week. I think I'll get them up. But if you want them in your region where you haven't done them yet, maybe there's a specialist down in your area where we could work with, and to have all the techniques in the scripts written, and I could share that with whoever might be interested. Or if there's just one or two communities you're interested, give me a call. Maybe I could knock those out for you as well. That's really the end of my presentation, and just want to leave time for some questions here. So thank you very much for listening. I appreciate it.
Yeah, thank you, Rick. That was great. You did a nice job and clearly walking through the steps, and I'm already thinking about some implications. Although your last photo here is triggering some other questions about fishing that I will leave for another time. So we had a couple questions that came in the chat window that I'm actually going to turn to one from Mary about your modeling of the treated versus untreated stands. And there was another question from Devin, and I think the two are connected. So it's about your assumptions, and so Mary asked, is it assumed that there is an ignition and a consumption of 100% of available fuels in both the treated and the untreated stands for modeling smoke production?
No, it's not 100% consumption. Certainly, there's a lot of trees that are left, shrubs that are left on the landscape when we run both scenarios through the model.
Okay. And then related, in terms of the area, what proportion of the fire area did you model as treated for the fuel treatment comparison?
Now, that would be 100% of that area.
Okay.
Yeah.
So within the
that's
treated...
not really necessarily realistic. It was just an attempt to kind of bracket what we might be able to do, or even if that allowed our firefighters to get a place where we could then engage directly, because maybe the flames drop from the canopy down to the ground, and the flame lengths were such that maybe we could hold the fire at that perimeter and we wouldn't burn that area behind. So it might not be such a bad assumption.
Yeah, definitely there's a lot of nuance in what models we want to project out. And one of the things I like about your work is you took in the sort of smoke distribution, looking at, okay, let's look at a few actual fires. And I think there's a balance of modeling out and then looking at case studies. And let's see, so Gene had a comment here in the 90s and early 2000s. FETM was being used to show trade-offs of treatments in regard to smoke and target communities. And it seems that that was lost. Now the topic is coming back up. And so maybe there's some literature out there that we need to dig back out again. So thanks for bringing that up, Gene. And if you want to share any particular resources that you're aware of publications from that time, that would be great.
Yeah, a lot of that work was done through CH2M Hill.
Okay.
That's the fire effects trade-off model. And we were able to show exactly what you just talked about, the PM2 concentrations. It was following the mid-90s fires in the Wenatchee area, and Wenatchee was the target community, again, Seattle also. Very conclusive, just like the numbers that Rick has been throwing around. And yeah, it just seems like all of that, we were going great guns, and then it lost interest. And now here we are 25 years later, throwing the same kind of science back up again. And yeah, it just seems like, are we going to make it stick this time?
Yeah, great point, Gene. I remember a model, I wanted to say it was similar. It was a different consulting agency, Air Science, but Richie Herod on the Okanagan Wenatchee National Forest was involved with that.
Yes.
When I started on with the Forest Service, I tried to find that model and see if it was good. I guess Richie found some issues with that model. And when I talked to him, he said it needed some work, and then the contract ran out. Back then, there wasn't a whole lot of money to reinvest in that. So it didn't get, I heard it was a really good model and had some really looked at a much longer period of time with this trade-offs between prescribed burning, emissions, and wildfire, but it was too difficult to resurrect that effort. And we never had.
Yeah, you're exactly right. Yeah, it was Air Sciences. The last time I was involved with it, it was under the Air Sciences umbrella, and we were working with the Okanagan Wenatchee. In my humble opinion, I only have 50 some years in the business. It was very accurate for what we were trying to portray at the time.
Mm-hmm.
And we just couldn't get any political traction. In essence, what we were doing was showing air advisory not legislators, regulators, the trade-off of, okay, you're okay with having these wildfires choke in Wenatchee with this number of PM days, whatever, just like your data. And the trade-off would be if you did the same thing at a lesser degree on a schedule where we could tell the public when the smoke was coming. That was what the whole essence of the fire effects trade-off model was would you rather have half the smoke predicted in timeframes in order to eliminate a majority of the smoke from wildfires into the future? And apparently the public and legislators weren't ready for that at that point in time. And that's all part of why that whole Air Sciences thing just crashed and burned. And here we are 25 years later, and a new generation wants the smoke to go away.
I think you're right on, Gene. And right now, last week, there was a Government Accountability Office report that came out that basically had 6 recommendations. And it was for the administrator. 2 of them had to deal with the EPA and the Department of Agriculture, and a similar one for the Department of Interior that dealt with trying to align our goals in dealing with air quality and wildfire risk. And I don't know what that means yet in terms of things, but I think as we see these landscape evaluations coming out for a lot of areas around the country, and recommendations for how much area needs to be treated, we could look into those and see, is that realistic or not? And if it's not realistic, what the heck are we going to do? Do we stand on this alone? What could the EPA do? And I think it really takes maybe some new direction from EPA or allowances to work with us. And we might have to go through the exercise of demonstrating the risk from the wildfires are worse than the risk from the prescribed burning. And there's a lot of factors to consider in that. But if you want to talk about it more, perhaps we could talk offline. I'd be really interested in that.
Yeah, I'll give you a ping.
Thanks, Gene.
Okay, so next question we have, well, first of all, props on a really impressive fish in the picture there, Rick. So we've got that. I wanted to make sure you got that feedback. And the next question we have is, I keep hearing rumors of new EPA regulations that will make conducting prescribed fire treatments even more difficult. Can you speak to that?
Yeah, EPA, once every 5 years, they're required to review the National Ambient Air Quality Standards. And if the science supports it, to revise those standards. Well, currently, EPA has been reviewing the PM 2.5 standards, And they're talking about strengthening, their terminology, the annual standard and leaving the 24-hour standard unchanged. They're taking comments on both. So even if the 24-hour standard doesn't change in the annual standard change, everything that happens on the 24-hour, if you count the smoke from prescribed burns and they toss out the days with the smoke from the wildfires, we could easily have exceedances of the annual standard because of prescribed burning. Well, then what happens? They're going to ratchet down on prescribed burning more. So that makes it even tougher. And I think that's what that question is getting to. And our Washington office has been very engaged with the EPA and making them aware of this. And so have members of Congress that called out in that GAO report for EPA and in land managers to align our goals. We haven't figured out yet how to align our goals, but we just got to keep working together and kind of pressing the issue, and where the regulations need to change, hopefully they'll change. And where they don't need to change, let's figure that out too.
Okay. And sort of a related flip side of that question is, can you describe more how this model could be used to increase the pace and scale of prescribed fire?
I have other ideas on how to increase this pace and scale of prescribed fire, but it's not using this model. This was really to answer the another side of the question is, how do we reduce wildfire smoke, the smoke from wildfires in communities? And so I use it to identify where in the landscape we need to do fuel treatments. Now, there's a lot other aspects in dealing with increasing pace and scale. I think I'll just be very brief here. I think on each landscape, and let's talk about maybe at the watershed level, maybe the fifth. So not at the district level, but maybe in those large watersheds within a district level, we need to identify exactly how much prescribed burning needs to be accomplished and by when, right? And I think that's up to each district to get those numbers together. I haven't really seen them a whole lot, but if we have those, let's say we need to get 100,000 acres of prescribed burning accomplished. Let's say we need to do that in 10 years. I'd love to get that kind of data. That means on average, we need to do 10,000 acres a year. Well, how many opportunities do we have to burn each year? Well, here in the Pacific Northwest, when our fuels are and weather are in alignment and in prescription, a good day to burn, maybe it's only 10 days a year that we have. So that means we're trying to get 10,000 acres done a year with 10 opportunities. That's 1,000 acres of burn. And then I asked myself, is that realistic? We could go back and look at historic amount of burning or look how much in the smoke management plans, and that might not be realistic. And if it's not realistic, that's what I want to go talk to our air regulators and EPA and say, okay, how are we going to get this done? This is not just a land manager's problem. This is everybody's problem, because we know the smoke is everybody's problem, much bigger than just the footprint of the fire itself. So that's what I think we need to do internally to do that with the model. Maybe we could run this model reverse. I mean, in the forward direction, then to say, if we're going to do a 1,000-acre burn, where's the smoke going to be go that day? Is that community ready to receive smoke? Do they know about it? Do they have those means to protect themselves? Do we need to look for community grants to get more portable, high efficiency particulate air filters in place? Would we have the community support to do that? I think everybody's got to be convinced the risk from the wildfire is worse than the risk from the prescribed burning. That may or may not be the case in all areas. So still quite a bit of work to do along those lines, but I think that's where we got to go.
Yeah, thank you, Rick. And that's probably a good place to wrap up here. We're back at the top of the hour. I do recognize Tim had a question about wood quality reductions from prescribed burning. That's really, I think Tim and I might talk about that offline. It's a whole other topic, really. But I think it does point again to trade-offs, and that's a lot of what you're talking about here. I mean, you mentioned early in the presentation wildlife values with downwood versus smoke production. And again, you know, in this, as we think about land management, there are a lot of trade-offs that we have to consider. And I think that the tools that you're providing here aren't gonna make a decision about those trade-offs. That's not what they're designed to do. They're designed to help humans make better decisions and put more information on the table. And that's what I love about them. So I think it's a really useful perspective, and I appreciate some participants pointing out this isn't the first time we've thought about some of these trade-offs. Lot to digest, and this is just one more piece of the puzzle. So thanks so much for taking the time to share that piece of the puzzle, and I'm glad that we had so many folks on as participants, and I look forward to seeing at least some of you on future Southwest calls or on the Northwest Fire Science Consortium as well. So again, thank you so much, Rick. Thanks to all the participants, and we'll get a follow-up email with a recording out as soon as we can. So thanks so much, and have a great afternoon, everybody.
Thank you very much. Feel free to reach out to me with any follow-up discussion or questions.
Thanks, Rick. Okay. Have a good afternoon. Bye.